So we arrived yesterday, well, at a statement of the fundamental dynamical principle of quantum mechanics, the time-dependent Schrödinger equation here. I didn't offer any justification for this at this time. The justification or arguments which will make this seem plausible are about to come, but they have not yet come. However, we already, at the end of yesterday's lecture, realized that if the state of our system is such that the energy is well determined, the result of measuring energy is certain, then the time evolution of that state is absolutely trivial. The state evolves only in that its phase increments at a rate with a frequency, an angular frequency, e upon h bar, which is typically very large because h bar is very small. And we went on from that result there to show that the solution to this equation for any state of psi takes this form, that the state of the system at an arbitrary time is this sum over the states of well-determined energy, where an, as ever, is En evaluated at. So if you evaluate these coefficients at time t equals 0, or indeed at any time at your convenience, then just by inserting into this sum, this ordinary sum which we've seen a few times of psi expanded in terms of a complete set of states, if we just insert these exponential factors, bingo, we evolve the state according to that equation. So that makes these states of well-defined energy of crucial operational significance. And the result of that is that we spend a great deal of time solving the defining equation of these states, which is that HEn is equal to En. These states of well-defined energy are by construction eigenstates of the Hamiltonian operator. And this is the time-independent Schrödinger equation, to distinguish it from the time-dependent up there. So only states of definite energy solve the time-independent Schrödinger equation. Any state, the state of our system, always has to solve the time-dependent Schrödinger equation. So what we want to do now, the next item on the agenda fundamentally, is to provide some justification, make it seem plausible that that is the correct equation of motion. And a good way to do that is to link back to classical mechanics. So recall, classical physics is that limit where the uncertainty in the values of dynamical variables is sufficiently small that it isn't necessary to calculate the whole probability distribution. It's enough to know what the expectation value of the probability distribution is, because the true value will be very close to the expectation value, and we ordinarily don't distinguish between the expectation value and the true value when doing classical physics. So what we want to do is calculate d by dt of the expectation value of some observable, I think we're calling observables Q. And let's put an IH bar in front of here just in order to in order to simplify the algebra. So we're trying to calculate this, the rate of change of the expectation value of something. This something might be position, so this might be x, this might be momentum, it might be energy, it might be whatever you want to know, it might be angular momentum, whatever you want to know about the system. This would tell you the rate of change of the classical value of that variable, because the classical value is the expectation value. So what is that? Well, this is just a product. So obviously it comes into three parts: IH bar d psi by dt times q times psi plus, let's take the last bit now. Plus psi dq by dt. Sorry, these things probably should be where they're. Whether we make these things partial derivatives or total derivatives is of no significance. This is clearly a total derivative because this thing doesn't depend on anything except time. Whether we make these partial or total is very unimportant. So here we have an IH bar rate of change of psi, so this can immediately be replaced by H of psi. Here we have the bra psi, and the original equation. We can take the Hermitian adjoint of the original equation when it becomes minus IH bar d by dt of the bra psi. Curses, bra psi equals psi h. Remember the rule when we take Hermitian adjoints is we reverse the order of the symbols and we take the adjoints of the individual bits. H is an observable, so it's a Hermitian operator. So H equals H dagger. So I can pop those into here and here. So the first two terms give me, including the IH bar, this one is going to be minus psi h. So that is IH bar d by dt of the bra psi times q times psi. And this one, including the IH bar, this is going to be plus psi qh. And then we have a trailing bit here, which will be plus IH bar psi dq by dt psi. And these two can be handily combined together into a commutator because there's a minus sign here, otherwise the order of the q and the h are swapped around. So this can be written as psi, the commutator q comma h, psi, and then this is plus IH bar. Oops. So this result goes by the name of Ehrenfest's theorem. And it's one of the more important results of quantum mechanics. In most of our applications, we can forget about this, because what is this last term here? It's the expectation value of the rate of change of your observable. So if the observable was, for example, x, it would have no rate of change. X is x is x. It's always the same operator. If your observable were p, it would have no rate of change because the momentum is momentum is momentum. It doesn't change. Our understanding of what momentum is doesn't change from moment to moment. If it were angular momentum, it doesn't change from moment to moment. So this term here usually falls away. And so if dq by dt equals naught, which is the normal state of affairs, then we have that IH bar d by dt of the expectation value of q, which is often written like this in shorthand notation, right? We've left out the psi either side, just leave the angle brackets, which means the expectation value in any state whatsoever, is equal to the expectation value of the commutator q comma h. Okay, what does that tell us? It tells us immediately that if an observable commutes with the Hamiltonian, if Q commutes with H, that being the same thing as Q comma H equals naught, then clearly the expectation value of Q is always constant. And physicists are always very excited by quantities which are constant. So we call it, what do we call it in classical physics? We'd call it a constant of motion. Famously, Newton said that if you didn't go for messing with particles, the momentum was constant, or maybe he said the velocity was constant, right? So velocity is a constant of motion. We now would reinterpret that as momentum is constant. We often know that angular momentum of the angular momentum of the Earth is almost constant insofar as it's not acted on too much by the moon, and so on and so forth. So physics is full of constants of motion. They're very important. In quantum mechanics, there's a special notation around here, which is to say that we say that Q, the eigenvalue of this, is a good quantum number. So if somebody says that angular momentum is a good quantum number, they're simply saying angular momentum is a constant of the motion. We can go further than that, though, because so we've shown that the expectation value of Q is constant. We could show easily that the expectation value of Q squared is constant too. It's very straightforward. It's obviously the case because Q squared is an observable. If Q commutes with the Hamiltonian, then Q squared has to commute with the Hamiltonian. So Q squared is also a constant of the motion. That means that if you start, so this implies that if initially, if at t equals naught, psi is one of the states of well-defined Q, so QR, one of the eigenstates of the operator Q, so we know for certain the result of a measurement will be QR, then what does that mean? That means that at t equals naught, the expectation value of Q is obviously equal to QR, and the expectation value of Q squared is equal to QR squared, which implies that the variance of Q, that implies that the variance of Q, which is as ever defined to be the expectation value of Q squared, or minus the expectation of Q itself squared, vanishes. So this variance expresses, of course, the fact that there's no uncertainty in the value that we get. But since this is a constant of the motion and this is the constant of the motion, if this variance vanishes at t equals naught, it vanishes at all times. And the only way that can happen is if your system stays in the state that it was in originally. So if it was in a state of well-defined Q at the beginning of at t equals naught, it'll be in the state of well-defined Q at all subsequent times. So that's the meaning of this that's why people talk about good quantum number. If I know at some particular time that the angular momentum of this isolated body is h bar or whatever, then I know that at all later times it's also h bar. It's a quantum number worth knowing because it's always valid information. So we're very interested in quantities in observables that commute with the Hamiltonian. Let's move over here for the next point. Obviously, okay, so we're interested in things that commute with the Hamiltonian. And a trivial observation is that h comma h equals naught. This is a bad place, isn't it? I'm not sure there's anything we can do about it. So the Hamiltonian commutes with itself, which means that the expectation value of h is a constant if dh by dt equals naught. So now we need to come back to this point that I said usually it's going to be the case that the partial derivative of q with respect to time, I've lost it, it's up there somewhere, the partial derivative of q with respect to time vanishes. Now the Hamiltonian is an interesting case where that isn't necessarily the case. There are very important circumstances in which the Hamiltonian does explicitly depend on time. The expression for the energy depends on time. For example, if you if you put a particle in a time-varying magnetic field, the expression for the Hamiltonian, and the Hamiltonian is going to depend on the magnetic field, depends on time, and in those circumstances, the energy of the particle is not going to be constant. And the reason is you're working on that time depends. The Hamiltonian reflects the work that you're doing on the particle. But if the Hamiltonian is independent of time, so that will reflect you're not doing any work, and then the expectation value of h equals constant is conservation of energy. So this condition, it will turn out, is intimately connected to whether or not you're working on the particle. Now, let's have a look at the rate of change of the expectation value of any observable when we are in a state, when psi happens to be a state of well-defined energy. Right? So these states of well-defined energy, we've explained that they're the key to solving the central equation of the theory. So let's ask ourselves a little bit about those states. So the amplitude, let's have a look at Q E. Right? This is the amplitude to determine Q given that we're in the state E. Well, let's give it its n, Qn. So this is the amplitude to find the value Qn if you would measure with the observable Q, given that you're in a state with well-defined energy E. Let's work out the time derivative of this. IH bar d by dt of this quantity is equal to, this is so, it's very specific. dqn by dt. I wonder if we should turn this off. Is there any way we can turn it down? No. Let's try. It's not going to like that. Okay, so we do the same thing. This has to be IH bar thing we get from the Hermitian adjoint of the equation, and we get the time-dependent Schrödinger equation, so we get a minus Qn h, so that is that, and then we put E onto it, and this is going to be Qn stands by, while that, including the IH bar, produces an H E. And this is nothing very much, right? Because H works on E to produce E, because that's an eigenstate of H. E times the ket E bangs into this, produces minus E times Q and E. And this H produces an E, and so we get a plus E times Q and E. So these two terms cancel. So we've discovered that the rate of change of the amplitude to have the value Qn is constant. The rate of change vanishes. This amplitude Qn E is constant for any Q. So in order to obtain this result, we didn't make any restriction whatsoever on what the observable Q was. So the remarkable fact is that in these states of well-defined energy, if your system has well-defined energy, all its properties, the expectation value of every observable, and by thinking about, in fact, it then follows with a couple of extra steps, the probability distribution of measuring any observable whatsoever is completely constant. Nothing ever changes. So that leads to E being called stationary state. These states really are forever. They are completely eternal. They're completely unchanging. They are not of this world. Right? And in particular, you can never get a system into, it follows from this that you can never get a system into a state of well-defined position, because if it's going into there would imply that something was changing. But they never change. That's kind of a remarkable. So now we have a new topic, position representation. To bring us much closer to the real physical world, requires a bit of rejigging. So far we've used abstract representations. They're a little bit like the energy representation. Let's say we've assumed that our observable has discrete spectrum. So the spectrum is made up of discrete numbers. The thing about the position operator this is the thing made up of, this is the operator which encodes the states of well-defined position down the x-axis. It has a spectrum which is usually always continuous. It runs from -infinity to infinity. It's not discrete, it's continuous, and this requires some adjustment. So we used to write, we have been writing, let's divide the board, we have been writing that psi is equal to some an, shall we say, en. We use the energy representation. Now we're going to write that psi is equal to an integral, that sum over the discrete set of possible, the discrete values, numbers in the spectrum becomes an integral over the possible values in the spectrum, so that's from -infinity to infinity, of some amplitude, the amplitude to be at x, times the state of well-defined definitely being at x. So this is the state that the system is in when it is at x, when our particle or whatever is at x, and this is the amplitude to be at x, right? Amplitude to be at x, and this is the state of being at x. We used to have that En equals delta M. What are we going to have now? Let's draw this thing through by x primed, and we're going to have the integral dx primed, x primed x of psi of x. This side, oops, this side is clearly equal to psi. Sorry. And what do we want? What we want is that this, well, it's obvious that this thing vanishes except when x prime is equal to x, because if it's definitely at x, if it's definitely at x, then it certainly isn't at x prime if x prime is different from x. So this thing here is nothing except when x equals x primed. It must be non-zero and presumably rather large in order that, well, I think we can fill this in. This is, what is this? By definition, this is the amplitude to be at x primed, and I've already said that that is the amplitude to be at x primed. Sorry, x. So it's clear that this thing here is psi of x primed, the amplitude to be at x primed. So we have that the amplitude, the psi of x primed, that function, is equal to dx of x primed x of psi of x. And I hope that I'm sure you've already met this relationship of Professor Estley's lectures, that this can also be written as dx delta of x primed minus x of psi of x. So we have, so that result up there has been generalized or has morphed into the statement that x primed x is equal to a Dirac delta rather than a Kronecker delta of x minus x prime. we used to have that psi was the sum of the AN squareds was 1 by conservation of probability, that this was the sum of the probabilities to get the value En, and since you had to get some value, that sum of probabilities had to be 1. Now what do we have? What does this turn into? This relation here turns into psi should be 1, and how do we express it like this? We say that this is the integral dx of psi x psi. So here we're using the idea, that we used to have that the sum En was the identity operator. Now we have that the integral dx x is the identity operator. So all of these sums are turning into integrals. So this relationship becomes this because this is the identity operator snuck into there, and this is what is the amplitude to be at x, so we already call that the wave function of psi of x. This is the complex conjugate of that, therefore the complex conjugate of this, so this becomes the integral dx of mod psi squared. So the integral of mod psi squared should be 1 in this continuous ring. So these are just natural transformations of what we've already done in the discrete case to the continuous case. One more thing that we need to write down. We used to have that if psi was the sum AN EN and phi was the sum BN EN, then the complex number phi psi was the sum Bn star An, sum of n. Right? That's a result we have had. What's the analogous thing here? The analogous thing here is going to be that phi of psi is going to be the integral. Into here we stick an identity operator, the integral dx of ket x bra x. So this becomes the integral dx, so we stick an identity operator into that gap of phi x of psi. This is what we have been calling the wave function of psi of x. It is the amplitude to be at x, which is appeared as a function. It is a function of x, it's a complex number depending on x, psi of x. And by analogy, we should call x of psi, x phi, sorry, we should call the wave function phi x. That being so, this becomes the complex conjugate of it, and this becomes an integral dx. So that both of these things, of course, are functions of x. So this is precisely a transformation of that, where the sum, where n has been replaced by x, and the sum of n becomes an integral over x. So this is the stuff we have to do because the spectrum of x is continuous and not discrete. Let's just do a little practice with this by asking ourselves, how does the operator x work on an arbitrary state of psi in this representation? So what we want to know is, the thing to do is to ask ourselves, what wave function represents that? That is to say, what is this complex number as a function of x? So here's the operator x, here is an arbitrary value of x. I would like to know what the amplitude to be at x is for this state that you get when the operator x works on the general wave function x. When you see an operator x, the obvious thing to do is to stick into here an identity operator made up of the eigenfunctions of x. So in order to understand what this is, what we do is we slide into here one of these identity operators. X is busy, so my identity operator is going to have to be a sum of x prime, some new value, some independent value of x. X, x, x primed, psi. So here's the identity operator along with that. Now life is relatively straightforward because this is an eigenfunction of that operator with this eigenvalue. That's the definition of this element here. So when x meets this, it produces simply x times x primed, the number, times the ket x primed. So this becomes the integral dx primed of x prime. There's the eigenvalue popped out. Then we have x primed. And this we recognize to be the wave function of psi evaluated on x primed. But this we recognize now, we've seen that this is the Dirac delta function of x minus x primed. So when we do the integration over x primed, this ensures that we get no contribution except at that split second when x primed is equal to x. And we get the value of the integrand evaluated with these x primes turned into x. So this is equal to x from psi of x. So at the end of a long story, what have we discovered? We've discovered that the wave function associated with the result of using the operator x on some state is simply x times the wave function of the original state. We can express that, but the way to remember that is to say that the operator acts on wave functions by ordinary multiplication. So you don't usually go through this kind of performance. You know what's going to happen when you do it. But that's the logical basis for this statement. Let's introduce another very important operator, the momentum operator. Now I'm going to make an unsubstantiated claim about what this operator, how this operator looks in the position representation. I don't expect you to think, aha, that makes sense. It doesn't make sense. It's a complete leap in the dark. We will understand later, considerably later, why these operators take the form that they do. But I hope soon to build confidence that it makes some kind of sense. But what we're going to do just right now is a complete leap in the dark. I'm going to say, well, let's investigate the operator. I happen to know it's the momentum operator, but let's investigate it, which is defined thus. Now let's just make sure we understand quantitatively what's happening here. An operator fundamentally is something which turns a state into another state. When we're in the position representation, we are we're working with functions. Our states are represented by their wave functions, which is the amplitude b at x. So the x operator has to turn a wave function of psi into some other function, and look, x of psi is another function. It depends on x in a different way from the way psi does. So similarly, this operator I claim is the momentum operator without any basis. I'm going to try again. This momentum operator is is turning the wave function of psi into its derivative. A derivative is a function different from the function we first thought of. So indeed, it's turning a function into a function. So that's kind of, it means it is at least a valid operator. Is it Hermitian? It's not obvious that it's Hermitian, and if it isn't Hermitian, it certainly can't be the momentum operator. So let's check that out. So let's write down the complex number phi p hat of psi. Let's evaluate this using this hocus pocus here, all right? So this is the integral dx. What am I going to do? I'm going to put an identity operator just in here, made up of x's, right? Why? Because I know I've defined p in terms of what happens when it has an x on the left of it. So this is going to be phi x p hat psi. And now we can turn this into wave function language. This is the complex conjugate of the wave function phi. So this is the integral dx of phi star of x. And we've defined what that is. It's minus I h bar d by dx of psi. So we can now integrate by parts. We're integrating minus infinity to infinity. So we can integrate by parts this partial derivative to get this partial derivative of psi and onto the phi. So what does that give me? We get a square bracket term. We have a phi star. When that wretched minus I. Let's put the minus I h bar outside some vast bracket, right? So we're going to have a square bracket term now. We're going to have an psi star. Sorry, a phi star of psi minus infinity infinity, and then we're going to have minus the integral dx d of psi. Sorry, psi d phi star by dx. Close the big bracket. So we're going to operate under the assumption that this thing vanishes. Now this is a rather hairy, don't press too hard as to whether this really does vanish, but the general idea is that the amplitude to find your particle at the edge of the universe is 0. So we dispose of this on the grounds that it is the amplitude to find the particle infinitely far away. We're going to say that that's 0. We will actually be working, you'll see quite soon, with some wave functions where that doesn't vanish. And this is an example where physicists are rather fast and loose. But fortunately, this doesn't lead to any bad effects. So this we put in the bin. And this we can see is more or less what we want. Let's just tidy up a bit. So what is this that survives, including this minus IH bar? So we're going to have a minus, well, let's leave the minuses out. Dx of a psi, and then we're going to have an IH bar d phi by dx. Supposing I take the star of all that, then I think I need a minus sign, because this minus will cancel on this minus. So we'll have an IH bar times this stuff with psi starred. If I take that psi, that star, and put it around the whole caboodle, including the I, I'll need an additional minus sign to cancel the minus sign that will arise when that star is evaluated on here. And I can say now that that is the integral dx of psi star minus I h bar d phi by dx star. So if I take the star, this star, completely outside the whole thing, then psi will need a star, which will be cancelled by the global star, and otherwise everything will be okay. And what is this? This that we have in here in Dirac notation is a psi p hat phi, and that star sits outside. Right? What's inside the star is by definition this. So there we are. The answer is it is Hermitian, provided we get rid of that surface term, that minus infinite, the square bracket. One more. Okay, let's calculate the commutator x hat comma p hat. We're going to calculate it like this. So what we're going to do is calculate the action. So what we know at the moment is the action of p hat on any wave function, and we know the action of x on any wave function. So I want to work with wave functions, which means I put a bra at this end here, a bra x at this end here. And what does this give me? So this is going to be, obviously, x hat p hat of psi minus x p hat x hat of psi. No prizes for that. Now, this, we've discovered x on this. We've discovered that x on any wave function, on any object, gives you x times the wave function you first thought of, the wave function you were operating on. What is the wave function that this produces? The wave function that this produces is minus I h bar d psi by dx. So we merely have to take that and multiply it by x, and then that's what you get there, right? This is a complex number depending on x. This is a complex number depending on x. So p on this is a certain wave function. It's this. And then x hat on that produces x times that wave function. So that's it. So here, same stuff. X on this is going to produce x of psi, and then p on that is going to produce minus I h bar d by dx of that stuff. And there's a minus sign floating here. I mean, this minus sign is this. That minus belongs to the p operator. So I think you can see that the x d psi by dx terms, when you differentiate out this product, you'll get two terms. You'll get x d psi by dx, which will cancel on this because of the two minus signs. And you will also get an psi times the derivative of x with respect to x, which is obviously 1. So we're going to get I h bar of psi of x, which can also be written as I h bar x, of psi. So what have we learned? What we've learned is that for any state of psi whatsoever, we never said what it was, the wave function associated with xp of psi is simply I h bar times the wave function of psi. So that means that we can now write down an operator statement that x hat comma p hat is equal to I h bar. So the commutator of these two operators is a constant, small constant, but constant. And a commutation relation of this sort is called a canonical commutation relation. We will meet other relations of this type where the commutator of two operators is equal to I h bar, and they will be declared canonical as well. The word, this canonical, of course, comes from classical mechanics, Hamiltonian mechanics, and this arises because in classical mechanics, momentum is canonically conjugate, quote unquote, to x. Right. So now that we've done that, let's, we've just got time, I think, to do this. Let's apply Ehrenfest's nice theorem to, let's work out this, I h bar d by dt of the expectation value of x. What do you think this should be? The rate of change of the expectation value of x should be the speed, right? Did I say that right? The rate of change of the expectation value of x should be the speed, velocity, whatever. So we're hoping that this turns out to be I v, which should be I p upon m if we're doing this right. According to Ehrenfest, what's this equal to? It's equal to a psi x hat comma Hamiltonian of psi. Right? That's Ehrenfest's theorem. Concrete example of, application of. So in order to go further, we need to say, so what's h? H is the energy operator. What do we know about the energy of a particle that's moving in, possibly with some potential present, right? So the energy should be a half, classically, perhaps if we're doing this classically, I should replace this with an energy, should be a half mv squared plus the potential energy depending on x, which could also be written as the momentum squared over 2m plus the potential energy, right? Because P classically is mv. So let's suppose that we can carry this forward into the quantum domain and say that the Hamiltonian operator is the momentum operator over 2m plus v, the function v evaluated on the position operator. Then we're going to have that IH bar dB dt of the expectation value of x hat is going to be the expectation value of x commuted with p squared over 2m plus v but we know that this commutator can be broken down into a sum of two commutators. The commutator of x with p and the commutator of x with v. But v is a function of x, and therefore x, the position operator, is going to commute with this. So we're going to have that x comma v equals naught because v is a function of x. So what we're left with is the expectation value of expectation value of the commutator of x with p of psi over 2m. Okay, I can take the 2m out of the commutator because it's just a number, and I can express p squared as pp, but we discussed probably yesterday how we took the commutator of a product. We used a rule analogous to differentiation of a product. So this is equal to a psi onto x comma p commutator p standing idly by plus p the first p standing idly by while x commutes with the second p. But we've discovered that this animal is IH bar, right? This is IH bar, and this is IH bar. IH bar is just a boring number, so it can come out front. So that becomes IH bar over 2m. And then we have p plus p, which is 2p, so I can rub out that 2, times so what have we discovered? We've discovered that we can cancel this IH bar on the right side with what we had on the left side and say that dB dt of the expectation value of the position is in fact equal to the expectation value of the momentum, what I claim is the momentum anyway, over m, which is exactly what we were hoping for, right? So we have recovered the definition, well, the relationship between velocity and momentum, which in Hamiltonian mechanics is a rather, those of you who've done S7 will realize that the connection between momentum and velocity is not as simple as elementary Newtonian mechanics would lead you to believe. It can be quite subtle, and it's determined by this, which is this is one of Hamilton's equations. What we've done is derived one of Hamilton's equations which supersede Newton's laws of motion in classical physics. So we derived from quantum mechanics a classical result which was already known, but this is the justification for Hamilton's equation. It's because this is true that Hamilton's equation is true. And we'll leave it on that, and tomorrow morning I'll start by deriving the other of Hamilton's equation, which is analogous to F equals ma.